Yeah, welcome back. Today will be the first workshop of McMahon 2023. We have the pleasure to have Zahra Azizi, Dr. Zahra Azizi here. Yesterday was our opening ceremony, and unfortunately we had this Zoom hiccup that we had a 100 people limit. So some people were locked outside. So if you were one of those people, we're very, very sorry again. We sent you all of you an email yesterday to explain the situation and sent you the correct Zoom link today. And if you have registered on both Google form, which had led you to a Eventbrite link, that would you will have already received regular emails from Eventbrite, which I think is how you got here as well. So just for the people that weren't able to make it yesterday, from the beginning of today's talk, I will take 5 to 7 minutes to explain the housekeeping again before Dr. Azizi starts her workshop, just to fill everyone in. Yeah, and right, let me start. Oh, yay. It finally exceeded the 100. It means it worked. Awesome. So we don't have the same problem as yesterday anymore. So I would just start sharing my screen and explain everything. All right. Welcome, everyone. As I mentioned today, the topic will be Introduction to Classical Machine Learning. And we have our great instructor, Dr. Zahra Azizi, with us today. She was also a part of us last year as well. So welcome back. Just a little bit of housekeeping for communication. Please feel free to send us an email at mechhacks2021@gmail.com if you have any questions. And in the email yesterday we sent, we also included a Discord channel link. So if you can see my full screen, you'll be able to see the McMahon Hacks channel. And then inside there we have, oh, seems like people have already joined. We had the different channel for every year. So this year is the 2023. We have the workshops and seminars and general questions, sub channels there. You can feel free to ask a question. Just if you weren't here yesterday, I just wanted to reiterate that we started in 2 years ago with the inspiration of teaching about deep learning in the context of medical image analysis and radiation oncology. And this year, as we all know, the advancement of AI is extremely fast, and large language models and everything is taking over. And that's, and the clinical world doesn't escape that as well. So for the second phase of our program, we'll start introducing more of the state-of-the-art methodologies, and including text analysis as well, that can hopefully be applicable to your daily work and research. And I just also please want to respectfully ask everyone in the audience, if you can mute yourself, that would be wonderful when our presenter is speaking. So, and then just to reiterate our program structure is that we have seminars and workshops live always on the weekend. Yesterday was our opening ceremony at 10:30 a.m. Saturday, Eastern Daylight Time, and workshop is on the Sundays live at 10:30 a.m. Eastern Daylight Time. I will provide the Google Colab code and everything on the Gumroad platform that we have set up. We also have offline help on the Gumroad that you may have asked to, you were asked in previous emails to register and create an account for. So just if you didn't do that, you were in one of the emails before, you were led to go to this link, and then you can just put 0 here and click I want this. You'll be able to see a platform of all of the materials of our program there, and we will upload all of the sessions after they're recorded as well. All the sessions are recorded, no worries about that, and then we put it on our YouTube unlisted, oops, not this one, a listed YouTube playlist. This year is called McMahon 2023, and you'll be able to see the opening ceremony here if you weren't able to join yesterday. So this link is commonly shared in our conclusion emails every time. So, and then every week we will have mentor tutorials, and this week we'll actually have our own Hossein Jafarzadeh as our mentor this week on Thursday at noon Eastern Daylight Time, if you have any questions, so you can go ahead and ask. Just to reiterate, for the new parts of this year, we divided the program into 2 parts. So last year we had still 8 weeks. So this year, because we want to try to incorporate new methodologies, state-of-the-art things into the second part of the program, we try to put some of the preparatory stuff as online modules on Gumroad. And week 1 to 4, you'll be able to learn about the fundamentals in medical imaging and deep learning. But the second part of the program will be more focusing on more advanced methods. And then we'll be able to, if you follow through the program, we'll provide certificates for both phases, and they're independent of each other. And we'll also upload all of the Gumroad things on online modules that you are expected to learn at your own pace that are during the week on Gumroad, so you can watch them over. They're mostly materials that are derived from the previous 2 years that we didn't feel the need to, do all of them live again. We only do the live stuff necessary on the weekend, but you need to familiarize yourself with certain topics before them. For example, next week when we actually start with the medical imaging applications with deep learning, you'll need to have some familiarities with basic image processing, medical image processing, and pre-processing, and that's the kind of stuff that's included in the learning your own pace modules that you can find on Gumroad. So just to reiterate, we're here today, Introduction to Classical Machine Learning. Starting from next week, the live session will be about, deep learning model training and evaluation. We're introducing PyTorch. So in this week between, you'll have some stuff to look over. And from there on, we'll go into the fully supervised mode of medical image segmentation and then transfer learning in medical image analysis. So ending here, we're concluding phase 1, and starting phase 2, we'll go into more advanced methods such as self-supervision, natural language processing, transformers, and best practices and generalizabilities in modeling. And just to show you a little bit of statistics of this year again, and we're very excited to have all of you from more than 50 countries again, from all these kind of different disciplines and from many, many different institutions and many different mother tongues as well. If you have paid for this program this year, you were probably a working professional or a professional in training. The rest of the program for students in training and for low and middle income countries for this program remain to be free. Yes, so this is our team again. We had Dr. Shireen Enger, who will have time to speak next Saturday, who's the director of our medical physics program at McGill, and working at Jewish General Hospital, Lady Davis Institute, and Dr. Farhad Maliki. So if you were here yesterday, he talked a little bit about some current states in AI and the education and how we can learn there as well, and Dr. Miriam Dutra. And this is my wonderful colleagues and friends from my own lab that are responsible for different aspects of McMahon. We had Alana, Juan, Laya, Parsa, and Herschel, and Mode. And then this is us. So you'll see myself here and Luca, who has graduated, but we still want to acknowledge him, and Hossein and Sebastian, who will be co-general chairing with me on this program this year, and they're here currently in the audience right now as well. And Hossein is our mentor this year on Thursday at noon. So now I have finished my 7 minutes of spiel of catching up everyone, so you didn't miss much if you, oh, well, we had a wonderful speaker yesterday at the opening ceremony, Dr. Steiny Corman, and she talked about a full workflow of AI segmentation and implementation in the clinic. So please go ahead and watch the opening ceremony recordings if you are interested in that. So now it is my great pleasure to introduce Dr. Zahra Azizi. She is a medical doctor and clinical epidemiologist, currently working as a postdoctoral fellow at Stanford University, focusing on digital health, computer science, and artificial intelligence in medicine. Her research goals are integration and practical application of computer science and artificial intelligence methods in medicine to produce new knowledge and deeper understanding of health-related issues, which ultimately aims to improve patient care and decrease disease burden. It's so great to have you back this year, Zahra. Please go ahead and start your workshop. And just for everyone else's knowledge, we will record all of the sessions and put it on YouTube and put it on the Gumroad platform, and as well as Zahra's Google Colab. So great, go ahead.
Amazing. Thank you so much, Eugene, for a great introduction and presentation. Okay, so today we are going to discuss a little bit of introduction to classical machine learning. And sorry. Okay. Everybody sees my slide now?
Yes, we can see your mouse moving as well.
Okay, perfect. So today we are going to learn about what is machine learning in general, different types of machine learning algorithms, supervised and unsupervised, and finally, what are the metrics that we can evaluate these algorithms, and at the end, we are going to discuss an example of the most common ML model for analysis and some of the like codes that we can go through our Google Colab together. Okay, so one thing that I wanted to, before going through the lecture itself, I had a recommendation was to break the vicious cycle and try to start your project. And while you learn from all of these courses, it's very important to see the application of all of these while you code, and you can learn a lot while you start your own project from your own errors. So that's very important to start as fast as you can. And one disclaimer, this workshop is mostly introduction to the subject. So we start from basic to more detailed for broader audience. And we don't include data cleaning methods. So one most important part before running machine learning algorithms is to clean the data, to understand the question, and to understand your data. And that usually takes a long time. And after that, we can run our models. So it's very important to consider that before starting any ML project. Okay, so what is machine learning? So as you see here, the difference between humans and computers is that humans, they learn from experience, but computers need to be programmed and given instructions, and they learn from data. And so that's precisely the definition of machine learning, and how we should instruct these machines to learn from our data is the important step. Okay, so here I'm just going to show you a cheat sheet for different machine learning algorithms. It really depends. So supervised versus unsupervised machine learning is when we have a labeled data and we have a target attribute. We use supervised machine learning, but when we don't have labeled data, we use unsupervised machine learning. So unsupervised machine learning can be used as for dimension reduction. And this is one example is PCA models, or they can be used for grouping of your databases, similar to what we do in clustering. And for the data that is labeled, if the outcome variable is a binary or categorical variable, we use classification models. And if we have a numerical variable, we use regression models. So now we want to go through unsupervised learning, and some of the examples of most important examples for unsupervised learning. So as I mentioned, unsupervised learning can be used for dimensionality reduction. So that's for reducing the number of input features in the data set. And, oops, sorry. And also for anomaly detection. So if you have outlier in your data, you can use these type of models to detect that, and for clustering. Now for the dimensionality reduction, one important example is principal component analysis. So I just want to give you an overview of what is PCA and how do we use it. So I'm going to start with a problem. So we have these bunch of group of friends, and we really would like to take a picture of them. So the question is from where we can take a really good picture so what is the best angle to take this one picture that can cover like most of our friends? So we try different angles in here, one from top, one from here, and then from here. And that's where we can see like that's the best angle that we can find. So now if this is one of the definition of how we look at the data, in which dimension we can get the most information from our data. Now let's try it on some dots. So in here is the same example. So we want to project these, we want to look at these dots, in which angle we can find the best location for projection of these dots. So we draw a line here, we look at these dots from here, and then we try this line in here to see if we can look at our data. And as you see, if we want to compare these two together, this one, the one on the right, has the it shows you a better, more information, better information. And in here, you chose a dimension that shows the better scatter of your dots. Another example is you have a housing data set. So these are your variables. You have the size of the house, number of the rooms, number of bathrooms, schools around, and crime rate. So you want to create a model, but you don't want to put all of these in your model. So this is a small example of PCA. Usually with your data, you will have like 100 columns, and you want to reduce that number. So how can we reduce the dimension of this? Like this is a very small example, but how can we reduce the dimension of these columns in your database? Do you have any suggestions how we can categorize them to reduce the number? Do you see any similar trend in each of these variables? You can reply in the text. Size and number of the room, yes. So that would be, and then what's the other category? So we can, number of bathroom, okay, size. So as you see here, we can divide between two main components. One of them is size feature. So size of the house, number of the rooms, number of bathroom, all refer to the size of the house. The schools around crime rate, they actually refer to a location. And by dividing these, you can see we can reduce the dimensionality of data from 5 columns to 2 columns. And you can use either of these that represent the size of the house. And you don't need to actually use all of them in your model. So that's one way of reducing. And in a bigger scale, when you have your real data set, this can mean a lot. For example, like you will have 10 or 20 factors related to the size of the house, but you just need one of them or two of them. And that with PCA, that's how you can reduce these numbers. So you can put the one that is most important in your model. The next unsupervised learning is clustering. So with clustering, what we want to do, we want to group the data. And so one example that I want to bring here is that we have an app and we want to do customer segmentation. Our goal is to make 3 marketing strategy for our app and see who uses our app the most. So this is our information. So we have age information and also the time that they have been engaged with the app throughout the week. How can we categorize these people so they can show a similar trend? So in here, we can say, okay, these 2 people are very similar. So they have one day engagement. They are very similar age. The other one is like this, but we can do this like over and over by hand. But how can we do this automatically using computers? We can plot them. If you plot these factors based on age and their engagement, you can see 3 important categories. So here we have age group between 18 to 23. They have very similar engagement. They have low engagement. Here we have age between 37 to 42. They have high engagement. And when we have older age, more than 50, we have low engagement again. So this is how we can group our data together and to study them within these groups. So this was some example of unsupervised learning. So there are different methods for unsupervised learning. Like for the clustering, we have k-means clustering, we have hierarchical clustering, and that by its own, it has a different workshop. It should have different workshop. But now supervised learning. What is supervised learning? In supervised learning, we have a labeled outcome. So our outcome is either a binary variable or it's a class or it's a numerical variable. For the binary one, we use classifications. For the categorical ones, we use classification. And for the numerical ones, we use regression models. So what is linear regression? Imagine that we have these dots and we want to find a line that best fits through these 3 points. So obviously we can try different lines like this. So first we try this and see if this fits. Like we can try it like different times and draw it randomly to see which line fits better. But in order to see how good is each line is, we need to calculate an error. So this error will look at the length of the distance from the line to these 3 points. And we can compare this error to find the best line that fits the best, like these 3 dots together. So this is the first line that I drew. And when I add the error, this is the error of the red lines. Now I change my line. so the error will increase. And then here I drew another line, and you see that it seems that it fits better compared to the previous ones, and my error also decreased. So now, if you continue doing this for several times, you will decrease the error until you reach a good solution like this. And from this line, this is called the one that best fits, has the minimum error. It's called gradient descent. And that is generally named as the least squares for linear regression. So what is gradient descent? Gradient descent, imagine that you want to go from Mount Everest, from top of the mountain to down here. And this resembles your error. And down here, you have the minimum error. And up here, you have the more. If you go to the right, your error decreases. If you go to the left, the error increases. So what you do, you come down, and that resembles the line that we drew before. And you see, when you come to the down, below to the mountain, your error reaches the minimum, and that's the gradient descent. You reach the best line that fits your data. So for the line that we showed before is the linear regression, the linear relationship between the dots. But in real life, most of the relationships are more complex compared to just the linear relationship. So we have cubic relationships, we have you see like this convex sign. So finding these is also very important to find the line that best fits your database, your data. And so this was the definition of regression. Now we go to classification. Do you have any questions from the regression or unsupervised? Okay, nothing yet. So next is classification. So with classification, in opposite to regression, we want to, we have a binary outcome, and we want to draw a line that divides these two type of responses together, these two, like the blue and green ones. So there are different types of classification models. One of the very basic ones is a naive bias. So this is for detecting email spams. So we want to build an email spam detection classifier that finds the spam in our email in the future. So in order to do so, first, we look at our previous data. Our previous data is 100 email that we already looked at them. We have flagged these emails as a spam, and these are 25 versus 75 of them as non-spam. And then within the spam ones, we try to find a keyword that is commonly repeated in our spam email. We find that word cheap is the most common word that has been repeated in most of the spam emails. And 20 out of 25 in a spam folder, and only 5 in non-spam use the word cheap. So this is the keyword that we want to focus now to build our classifier. So now, if an email contains the word cheap, what is the probability of the email being a spam based on the information that I just gave you? exactly 80%. So if we have the word cheap in our email, the chances of having the chances of our email being a spam based on this information is 80%. So here, this is one of the classifier that we identified. This is the probability of word cheap. But now I want to add more words to be able to define more spam emails. What do? I try to find more words that have been repeated in our spam folder. I found out spelling mistakes are the probability of being in a spam folder is 70%, missing title 95%. So when I want to look at our email and see if one email is a spam or not, what do is combine these features together to guess if they're spam or not. And this algorithm is known as naive Bayes algorithm. So one important assumption of this algorithm is that independence between predictors. And as we know in real life, it's very hard to find predictor variables that are independent from each other. So that's why this model is very limited. And also, for example, this model can be used for real-time prediction because it's super fast and it can make predictions in real time. It can also do multi-class prediction. And for example, in NLP model, when we want to predict like a multi-class text inside the NLP, we use this naive Bayes algorithm. And also for sentiment analysis and text analysis, text classification, we use the same algorithm. And what are the pros and cons? So as I mentioned, it's easy and fast. So for fast real-time analysis, we can use this model. And the assumption is that this independence, this makes it better than other algorithms. But what are the cons? So if our categorical variable has a category that was not observed in the training data set, then the model, our model will think that will assign 0 probability for that variable, and it's unable to make a prediction in our test set. So this is a phenomenon that is usually called as zero frequency. And to solve this, we can use some smoothing techniques. For example, we add a certain value to all of our features to the probability. It doesn't change the probability of other features, but it removes that 0 probability from our feature list. So that can help. That is the simplest technique that we can use in case of zero frequency. And also, naive Bayes is also known as a bad estimator. So the probability outputs from predict probability are not really taken seriously in this model. And another limitation of this algorithm is that the assumption of independent predictor, because in real life, it's very hard to find a set of predictors that are completely independent from each other. So these are some of the limitations of this model. Now, the most common logistic regression. So what is logistic regression? Imagine that we have these dots, green and red dots, and we want to separate these dots from each other. You see, we need to create a line like this, like before, to be able to separate this. But you see that this line hardly can separate these variables. What we do, you see in here, there are 2 errors have been made by this line. So the green one has been in the red space, and this red one has been in the green space. We change our line, and now the error has been 1. And change it one more time. And you see here that is we can draw the perfect line that can differentiate these dots from each other. And same as linear regression, the minimum, so the least error in here is not called gradient descent, is called log loss function. So it's the function which assigns a large value to misclassified points and a small value to classified points. Now in here, if we want to separate these dots from each other, you see it's very hard to make it with one line. It's almost like a, it should be like a curve. What we can do here, instead of one line, maybe we can draw two lines. And with these two lines, we can separate the green dots from the red dots. And so we can use the same idea as the gradient descent to minimize the log loss function. And this model is called neural network when we draw more than one line to divide our data. And the reason is this idea is very similar to real neurons that they get, that's why it's called neural network. So if we want to just give you an example, so the logistic regression is like one ninja drawing one cut through these dots, but neural network, we have multiple ninjas that draw the cut and can separate out the different dots from each other. The next type of classification algorithm is support vector machine. So again, let's look at these dots. If we want to separate these dots from each other, we can again draw a line. But which line is better, the yellow one or the purple one? Because both of them have been dividing these dots from each other. So both of them are practically good. So we measure the distance again. And in here, we see that the purple line is better than yellow line. The reason is if you wiggle the yellow line a little bit, what happens is that some of these dots can fall into the other side of the line. So there is, so it has high risk of error compared to the purple one. So in here, what we want to do, we don't really, we want to draw a line that is too far, has the best destination from the line, from the points. And so if we change it a bit, there is a least error for misclassification. So this method is called support vector machine. And so with this, we can give you an example of a surgeon who wants to make a cut. So these, this space is the best cut that the surgeon can do. But sometimes the line is not enough because we cannot really separate these dots from each other with a line. In here, it's a curve line. It's not a linear line. So let's think out of the box. How can we split these dots from each other? And to be able to separate them out. What we can do, we can imagine them in a three-dimensional space. And instead of drawing a line, we can draw a plane. And here, you see that with this plane, we can separate these lines from each other. So the curve in here resembles the plane in the three-dimensional space. That is called kernel trick. So again, with the surgeon example, how can she make a cut in here that separates the apples from oranges? Again, she can move the apples up and oranges down and make a cut here. So this idea of a support vector machine is that to create this cut that is called optimal hyperplane, that that create a maximum margin between each of these points. So these points don't fall out to the other side of the plane. We can have either, if it's the hyperplane, if it's, we can really divide the dots with a one line, is called the R2 dimension, but when it's 3 dimension, it's the, we can divide it with a plane. And in here, you see the here the margin is very small, but in here the margin is very large. That's so this one is like compared to each other. What is the pro and con of this model? So it really works well with a clear margin of separation. It's effective in high dimensional spaces. And it's really effective in cases where the number of dimensions is greater than number of samples. And it uses subset of training set and the decision function that is called support vector. So it's very memory efficient. But what are the cons? This model really doesn't perform well in large database. And also it doesn't perform well when we have a lot of noise in the data and our target classes are overlapping. And this model also directly doesn't provide probability estimates. And they're calculated using an 5-fold cross-validation, but not itself. Okay, so the next algorithm is the decision tree. So for the example of decision tree, yes.
Yes, we have some questions. I think we can get them out of the way maybe before before the next part. We have a few questions from Greg and Abdelha. So Greg asked, does the term regression imply a least squares optimization method? This is one for the linear regression part.
Yes, that's for the linear regression part.
And then the second question is regarding the linear correlation of the data. Is there a minimum value for the coefficient of determination, the R squared, to be able to go ahead and be confident in the present results?
So I'm going to explain the RS square in a bit, but no,
right.
There is no minimum. So usually the RS square, the highest, the better, but sometimes it can be misleading because the RS square, if our dependent variable increases in the model, the RS square can also increase. It never reaches to 1, but it's good that we have higher RS square, but with the lower one, we cannot really give a cutoff that say this is the best. We should try like different models to see if we can, like any of our dependent variables can predict the variability of our independent variable. So that's the definition of R square. So the higher is better, but there is no minimum like that we can say that is for sure you're confident to present the result. Because in real life, like there are a lot of factors that you cannot really include in your model. That's why it never is going to reach out to 1 or like 9.99. That's hardly ever. But the higher, the better. Yeah, that's the definition. But I'm going to go through that, I think in the metrics slide later. I hope this responded to your question. Any more questions?
I think we're good.
Amazing. Okay, so the next topic is decision tree. So For the decision tree, I brought the example of Google app and App Store. So our goal is to recommend apps to our users and to see if what are the characteristics of people who use like these type of apps to be able to recommend it to the correct users in the future. So we have gathered a table of data in here to use to make the rules for our prediction. So in here we have 6 people, and we have the information related to their gender, their age, and the app that they use the most. For example, you can see the one that are lower than 15, they mostly use the Pokemon app, compared to WhatsApp is a higher age, and males usually use the WeChat. So how can we, when we look at this, how can we really stratify these based on gender and age to create our prediction model? So in here, between gender and age, which one seems more decisive for predicting what app will the users download? What do you guys think? Age or gender? Yes. So everybody's responding correctly. So age is the variable that can be decisive to stratify the users. So first we stratify our app based on their age. So if they're age less than 20, they're most likely to use the Pokemon app. And if they're more than 20, they're most likely to use WhatsApp or WeChat. And then the next, we can look at gender. So if they're female, they're more likely to use WhatsApp. And if they're male, they're more likely to use WeChat. So in here, as you see, we split our data based on these rules. And so for the next, for our, so this prediction model for our next users, we can predict that, okay, we can suggest the app, the Pokemon app to users that are less than 20, and we can suggest the WhatsApp to our users that are more than 20 and female, and WeChat to our users that are male and more than 20. And this is the definition of decision tree. So there are some specific terminology for decision trees. So the root node that you see on top, this is the starting node, which our tree starts, and it only has child nodes as after that. The red ones are internal nodes. So these nodes are in between root nodes and leaf nodes, and the green ones are leaf nodes. So these are the nodes at the end of the tree that they do not have any children after these nodes. And there are other terminology like decision node. This is when a parent splits into 2 or more children nodes, then that node is called the decision node. Now there are some questions about decision tree. So how do we create a tree from tabular data? So usually with decision trees, we can use it for regression and also for classification. For regression tree is used when our dependent is continuous, and the value that is obtained by leaf node is mean response of observation falling in that region, and its prediction is made with the mean value. But then if our dependent variable in the training data set is categorical, the value obtained by leaf node in the training data is mode response of observations. And another question is, which feature should be selected as the root node? And what is the basis that should a node be, on what basis should a node be split? So this is to question all of these answers, we need to go through some of these important variables in decision tree. So Gini impurity, Gini is if we select 2 items from a population at random, so they must be in the same class, and probability for this, this is 1 if population is pure. So it works with categorical variable if we have successful failure, and it performs only with binary splits. And higher Gini value means we have more homogeneity in our split. Then we have chi-square. So chi-square is an algorithm that finds the statistical significance between the subnodes and parent node. We measure this by sum of squares of a standardized difference between observed and expected frequency of the target variable. Usually we select the split where the chi-square is maximum. Another one is information gain. This is one important one, because when we have a less impure node, it requires less information to describe it, and a more impure node requires more information. So information theory is a measure that defines this degree of disorganization in a system that is called entropy. If the sample is completely homogeneous, then our entropy is 0. And if our sample is equally divided to 50-50%, then the entropy is 1. So to calculate information gain, usually we choose the node with highest information gain for splitting. And for calculating this, we use entropy to calculate the gain. Another variable that is very important for splitting is variance. So variance reduction is an algorithm that is used for continuous target variables like regression. And this is used for, this is a standard formula that for variance that we can choose the best split based on this. And usually the node with lower variance is selected for splitting. Now, what is overfitting? So decision trees have a big limitation, that is overfitting. So if you continue splitting the tree, it can go forever and ever, like on your, if you have a big data. But there is a chance of overfitting, so it can find relationships that do not really exist in a general population. How can we avoid overfitting in our decision trees? So there are a set of constraints that we can put on our tree so it doesn't allow our tree to go further. The first one is minimum sample for node split. So we can define a minimum number of observation that is required in a node to constrain for splitting. And the other one is minimum sample for leaf node. Again, we define the minimum observation required in a leaf, so it doesn't allow to go further. Then we have maximum data of the tree, maximum number of leaf nodes, and maximum features to consider for a split. And the next important one is tree pruning. So in here with tree pruning, this is actually a real pruning. So we can this is the opposite of a splitting. So with pruning, we can remove the unnecessary leaves and have and avoid overfeeding in our model. What are advantages and disadvantages of decision trees? So decision trees are really easy to visualize, as you saw with our app example, is very easy to interpret. They're very useful for data exploration. They need less data cleaning, and but they have some disadvantages, including overfeeding and they're not really exactly fit for continuous data. Okay, our next topic, if you don't have any question, is now we are going to explain gradient boosting. So what is gradient boosting? First, we wanted to explain what is gradient descent. I explained it a little bit in our regression model, but imagine that you want to come from the top of the mountain to down to the lower point of the mountain. In which way do you move that you have the minimum cost or loss? That is called gradient descent. So the paths that have the minimum loss or cost when you come to the down to the mountain is called gradient descent. And this is important, especially in boosting models. Another factor in boosting models is learning rate. So again, the same example. What's your learning rate? What's the rate that your model is going to iterate is very important too. If you choose big learning rate, you might lose some information, but if you choose a small learning rate, you see that the model is going to run forever to find relationships, and it takes a lot of time, and there is a chance of overfitting. So we have to have a balance between these two about learning rate. Usually we start from higher learning rate to understand our model, and then we decrease our learning rate to optimize it based on our grid search. So what is boosting and bagging? The previous models that I explained were based on a single predictive model, like a linear regression that I mentioned, support vector machine, single decision trees. But bagging random forest and also boosting ones, they combine multiple models together into overall ensemble. And these usually, they combine predictions from individual base model that make up the ensemble. And they, since they are averaging the model, that reduces the variance. And that's why they're most effectively applied to a model that has low bias and high variance. And boosting, on the other hand, is very similar. So for building the ensemble in the boosting, it's usually it's a sequential, so it learns from the previous model, the previous error, and it iterates based on that. So random forests, they're built on ensemble of deep independent trees, whereas a gradient boosting machine, they're ensemble of shallow trees in sequence with each other, and they improve on the previous one. Here is another example of sequential ensemble approach. So in here, you see the main idea of boosting is to add new models to the ensemble sequentially. So you start from a very weak model, and then you continue and sequentially boost this performance by continuing to build new trees. And when you add each new tree to the sequence, it will learn from the previous model mistake. And then it can find the best relationship. This is another visual that it shows that. So in the beginning, this is the first tree that is very shallow. It's not really finding a relationship. But then when you go to the next sequence, you see at the end, it can find the best relationship. But if you notice here, around here, like this model in 256 tree, our model has really found the optimal relationship. So this is our best performance. But when you continue to more trees, you are increasing the risk of overfitting in here. Now, what are the difference between bagging and boosting? So bagging, as I mentioned, random forest is a kind of bagging, so it handles overfitting, it reduces the variance because it adds the trees together, it's independent classifier, whereas boosting, like gradient boosting, it has a chance of overfitting and it reduces bias and variance, and it's a sequential classifier. Now there are different types of boosting algorithms. So the base one is gradient boosting machine, but the most common one right now is the extreme gradient boosting machine, or XGBoost. We also have light GBM and CAT-boost. Light GBM is very similar to XGBoost, but it can be used for a very big data, and CAT-boost can be used for a categorical data. So now, what are the steps? So we learned about different algorithms, supervised and unsupervised. How do we start our model? So the first step is to pre-process our data set. As I mentioned, it's very important to clean your data and to understand your data to be able to find the best algorithm based on the type of your data. After you select your ML model, then we have to do hyperparameter optimization using cross-validation in order to avoid overfitting. So all these models, they have their own regularization techniques and hyperparameters that you have to optimize in a hypergrid. Then you have to divide your train and test. You should never use your test set, and you train your model on your train set. And after you find your optimal model, you test it on your test set to see model performance and also the accuracy of your model on the test set. So I'm going to go through XGBoost a little more, because our example for today is a model that has been run with XGBoost. So XGBoost has different parameters. The parameters are divided in 3 categories. We have general parameters, we have booster parameters, and we have learning task parameters. So general parameters are booster, silent, and thread. So booster is a type of model that you want to run. It can be tree-based model or linear model. And thread is actually used for parallel processing and number of cores in the system that should be entered. Then the booster parameters, these are regularization parameters. I have highlighted the ones that are important. Eta, alpha, lambda are for regularization. Learning parameters, so you need to identify your model metric and to assess your model performance based on these. If you have linear models and your outcome is continuous variable, you will use root mean square error, MAE, and if you have a binary model, you will lose log loss, area under curve, and for multi-class error is M error and M log loss. So there are general approach for parameter tuning. Usually, we start with high learning, as I told you. So high learning rate has a chance of, because it's going to produce shallow trees, it has a chance of not finding the correct relationship, but we start with high learning rate. We tune our tree specific parameters and tune our regularization parameters, including lambda and alpha. And at the end, we lower our learning rate, because with the lower learning rate, it's going to take a while to run our model. So at the end, when we find the best fit other parameters, then you can lower your learning rate. Here, I am just giving an example of overfitting. So here you see that our model is performing fine until you reach 300 estimator in here. You see in the 300 estimator, the error on the train set continues to drop, while the error on the test set is more or less remains stable. So that might be the sign of overfitting. And one way to avoid this is to use early stopping rounds and to stop execution once, and so that way you don't overfit your model. Then another way to avoid overfitting is to do grid search and using cross-validation. So with the grid search, as you see here, you can list different parameters for different hyperparameters in here to try your model in different steps. If we want to try all of these together, you will have 2,187 different models to fit if you want to try all of these combinations together. So what we usually do, we do randomized confidence interval cross-validation. So that way, it will randomly it will randomly run the model on the different combination of these hypergrids, and finally, it will give you the best possible model and the best possible hyperparameter for your model. And usually, we will assess the model metrics that I mentioned before, accuracy or area under care for the binary outcome, to identify what is the best model to choose the best hyperparameter based on that. Now, we talked about different models, but how do we interpret each of these models? So usually, the machine learning algorithms will give you model performance accuracy, but how do we interpret inside each feature of those models? So that's usually they call machine learning algorithms as a black box because it's very hard to understand the inner workings because of their complexity. But there are some interpretation techniques that helps us to understand the model, like the inside of the models. One important ones are feature importance. So it will rank the most important features in your model. Partial dependence plot will find the relationship that each feature has inside the model with the outcome. And there are other values like shape values that nowadays are really common to interpret our ML models. So here I'm going to give an example of feature importance. So feature importance is actually we'll try to find to rank your feature list based on different criteria. So it can be based on feature weight. So it gives a score that is calculated based on the number of times that the feature appears in the tree. It can be based on feature gain. So this score is calculated based on average gain of a splits which use the feature. And then can also rank based on coverage. So this score is calculated based on the average coverage, number of samples that are affected by the split, which uses the feature. Also, you can have your feature importance show as a tree. And partial dependence plot is very important. It helps you to understand the marginal effect of each feature on the predicted outcome. It really allows you to understand the direction of your features inside the model. For example, in here, you see that greater living area correlates with a greater monthly income. So you can see the relationship that each feature has within your model, and it's very important to understand that. ICE curve is very similar to PDPs, but PDPs, they average the predicted values across all observations, and they plot, but ICE plots, they plot individual observation level predictions. So each line that you see here is actually individual observation level prediction. But altogether, they actually are in very similar direction. Now, are there any questions? We can go to model metrics. And after that is our example. I hope that we are on time. Yes.
We did have a question on difference between cross validation and grid search, but I guess you're about to go into that with the evaluation metrics.
Yes, so we usually, our grid search can be done via cross-validation techniques. So that will test, for example, if you use 10-fold cross-validation, that will repeat your grid search 10 times in 10 different combination of your database. So that will really avoid overfitting. And it helps because if you only try on one sample, one like training set, you have the risk of overfitting. So when you want to try it on your test set, your model really doesn't work. But if you use cross-validation, it will test your hypergrid in 10 different samples, like 10 combination or 5 combination based on how many you choose. And then you have less risk of overfitting. Okay, so next is model metrics. So for classification and for regression, we have different model metrics. Is one grand rule is that you should never use your testing data for your training. So that's very important rule. And so I'm going to give you an example of a test that is going to diagnose a sick patient from a healthy patient. So our test can have a true positive value, false negative, false positive, and true negative. So here we usually create a confusion matrix based on our test results of true positive and true negative and false or positive or negative. So the first metric is accuracy. So accuracy tells us out of all of these patients, how many did we classify correctly altogether? So even sick or healthy. So in here, the response is 1,000 plus 8,000 to overall sample, which is 10,000. So we have 90% accuracy. But depending on your question and on your hypothesis, is very important to see if you want to have more, like if you want your test to identify more true positives or true negatives. So based on that, we can do some other tests to identify if our model is good or not. For example, if we have a medical model, we want a false positive is okay, but we really don't want to have a false negative. We want to find all sick patients, but if they are not all sick, is okay. But when in our spam detector model, we want a false positive is not okay, but we want to actually have if the model predicts false negative is okay. So you don't necessarily need to find all the spams, but you don't want your real email go to a spam. So depending on your model, we use precision or recall. So precision, it shows out of the patient that were diagnosed with an illness, how many of them were classified correctly. So our test was 55.7% had precision. And with the emails, out of all the emails that were sent to the spam inbox, how many of them were actually spam? It was 76%. But recall, it shows that out of the sick patients, how many of them did we correctly diagnose as sick? So it was 83%. And but with the email spam, how many of them were correctly sent to a spam folder? It was 37%. So you see, with the medical model, we really want to have a high recall. We want to identify sicker people. But with our spam detector, we really want to have higher precision. we want to find we don't want to send good emails to spam. What is F1 score? So precision and recall can, if we create an average of these two together, we can call it precision, and we can call it F1 score. So, oh, oopsie. So usually you see, even like when we created the average, the medical model was better compared to the spam detector on average. Now, model metrics for regression models. So for regression models, we have different model metrics that we can use. First is mean squared error, MSE. This is the most common metric that we use for regression. It is the average of the squared difference between predicted and actual value. And this penalizes large errors. If it's lower, the model is better. The next one is mean absolute error. So this is the average of absolute difference between target value and value that was predicted by your model. And it's not preferred in case where we have outliers. And MAE doesn't really penalize large errors. Now, the most important one is R squared, or coefficient of determination. So as I mentioned before, these metrics represent the part of the variance of dependent variable explained by the independent variable in the model. It measures the strength of relationship between your model and your dependent variable. And so the higher is better, but so the higher goes to 1. We never can reach to 1. If it's very low, it shows that the model does not present the variance of the dependent variable. And also one thing that we use, so R square, if we increase the number of our independent variables, the R square is going to automatically increase. What we do to avoid this false increase is to use adjusted R square. So with adjusted R square, what it does, it describes the amount of variance of dependent variable represented by every single independent variable, it represented by only ones that are significant in the model. So if you use the adjusted one, it uses the independent variable that actually affect the dependent variable. But the regular R square, it uses all of the independent variables. And the next one is root mean squared error, or MSE. So this is the square root of average of a squared difference of the predicted and actual value. So usually we prefer R squared error compared to this because R squared is a relative compared to RMSE is absolute measure. So we prefer R squared compared to this one. And also RMSE usually penalizes large errors as well. Okay, I think we are done. I can go through our example if you don't have any questions. I think we have 10 minutes left. All good? Okay, so the example that I wanted, is there any question?
Oh, no worries. I was just asking you, we had some Google Colabs as well, if you want to go through any of them, in case.
Yeah, absolutely. Yeah. I'm going to go through the XGBoost model together. So the database that we use in there is the census income database. This is a public database that you can download. I've put the link of this. Oops, sorry. It was this slide. No, this is slide. So you can download it from a link that I have mentioned in our Google Colab. And so in this data set, we have different variables like age, work class, education, marital status, occupation, race, sex, and at the end we have income. So our income variable is our outcome that we wanna create the model based on that and predict the outcome based on all the other variables. So let me stop sharing and okay. So I think you have this, our colleagues are going to share this with you. So we usually use Google Colab for our workshops, and you can try this right now or after the workshop is ended and ask your questions later on for our mentors. So you can download the data set from this link. After you download the data set, we can take a look at the data, to see what are the information, the type of the variables, which one are categorical versus which one are numerical variables. And you can also describe your data to see like their mean, a standard deviation, to understand your data set and to be able to create your model. That's very important part. The next step is to create pipelines. So I have two versions of this slides. One of them is for March 5th, but one of them is for last year's. I've created two types of pipelines. So this one is the one for March 5th is the easiest one. We want to create a pipeline for our categorical and numerical variables. And then at the end, we merge them together to clean the data. So the next part you will see like these transformations for changing the categorical variables, deciding what type of categories you want to give to your each of your variables. You can play with that on your own. And on the other version, there is like a pipeline that does all of these together. So there are two ways that you can try. After cleaning your data, next step, so all of these are the cleaning parts. Here. So the next step is that to create a train and test set model. So for creating your train and test set model, I've used 20% of our data as a test set. You're not going to use this for your training. And then you use XGBoost classifier because my outcome is binary and from the XGBoost package. At first, what we usually do, we create a default XGBoost classifier. So we don't give any hyperparameters. We just run the model in a very basic format to just understand the outcomes. And because our outcome is categorical, we use area under curve and error to evaluate our model. So here, we will assess our model. So this is our base model. We will assess it on our test set. And you see that even with that is without any hyperparameter, the model accuracy is 97% compared to test accuracy 86%. And the precision and recall are also presented on a F1 score for our test set and for train set. These are for test sets. Then the next step, I have created this graph based on our error and area under curve. As you see here, right in here, you see that our model is not really good. So there is very significant difference between the error in our train and test set. So here we have to correct this. So the next step, as I mentioned, is hyperparameter tuning. you run a grid search and cross-validation based on different hyperparameters. At first, we choose usually greater values of learning rate, so that your model can run faster, but then you can decrease that. If you increase the number of variables inside here, you have, like, your model can run for hours. So at the same time, we have to create tenfold cross-validation to avoid overfitting. So all of these hyperparameters are going to be repeated 10 times in our train set. And then at the end, it will give me the best score. So based on the best model from up there, I'm going to rank them based on area under curve. And I found out the best hyperparameters for my model to avoid overfitting. And you see here an estimator is 400. And so it's around here that the model should stop. Then we assess our model performance using our new criteria from the grid search, and our precision and recall, I think they have become better. The next step is interpretability. As I mentioned, feature importance is one of the most common interpretability techniques. So we can create plots based on feature weight, feature gain, or sample coverage. Based on feature weight means number of times that each feature appears in the trees, capital gain, financial weight, and also age. They are the most important features. Based on their split mean gain, relationship status, marital status, and education, number of years, they are the most important features. Here you can also create a tree of your model as well to understand it better. Again, relationship in here, number of education, and capital gain are the important features in your model. In here, I don't have the partial dependence plot. Let me see if we can have it in the previous year. No, I haven't included here. I will include that. So we can also understand like the relationship of each of these variables within the model. I will add it to your Google Colab to see what's the relationship of each of these important factors from feature importance within your model. Any questions up to here?
If you have any question, please feel free to put them on the chat.
Also, I have included, so I've shared two XGBoost models, and also I included logistic regression in here that you can run. Then also a decision tree, an example of decision tree, but the data set is different. And you can go through these, and most of them, they have explanation for each step. And then after you run this, you can ask questions from our mentors, I think on Thursday, or from me.
Yeah, we have a question about the train test split. Do you do the train test split before or after pre-processing? Alyssa asked.
So at first we should do pre-processing. We should clean the data. We should understand it. Then we do, before running the model, we do the train and test set split.
There was some question previously about, I think Eugene already answered, but maybe you can clarify again. Like, what is the difference between cross-validation and grid search?
So in grid search, you will try to find different hyperparameters to find the best model. But then with cross-validation, you will limit the risk of overfitting. So if you run the grid search without cross-validation, your model can run and find the best model that fits the best. I think I had one example that, but if you apply that in other data sets, it really doesn't work because of the overfitting problem. But with cross-validation, you are trying that grid search 10 times more, like in 10 different combination of data. So in that part, then you have a lower chance of overfitting with that. And if you try that and test it, you can find similar results. That's why we use cross-validation.
Thank you.
Thank you very much. Do we have more questions to Zahra? And if not, I would just like to show everyone the Gumroad platform one more time. So do you see my screen with the Gumroad platform? You do or no?
Yes, we can see it, but you are on the editing thing. You're not on the user tab, Eugene. But,
Oh,
but
okay.
that's fine. It's the
But
same.
that's fine.
Content.
You just need to refresh your page, and a lot of people were not sure about where to go. So right now we're in week 1, introduction to classical machine learning, and then here the good thing about Gumroad is that we can embed links so that we don't have to put it in the text file in the Google on the Google Drive, so you go find it. So here is a YouTube link of yesterday's opening ceremony, and then this is a zipped folder of 2 megabytes that you can the notebooks that Zahra has shared with us today that you can download and put it in your own Google Drive and run with a Google Colab. But what we've also done is to upload individually the Google Colab from here, so which you can directly click and then go into the Google Colab into from your own Google account. So it's the same as a Google Drive. So this is what Zahra just showed. What you should do is that you go in here because this is view only. So you go here and then go to File and then save a copy in Drive. So this will save a copy in your own Drive so you can run this code by yourself. And then we have the logistic regression code, the XGBoost, I think the linear regression. And then these 3 are the videos from last year for self-learning if you need more, if you need a bit more extra understanding on things. And just to let you know, next week because we're going into model evaluation and training, you should take a look at the image pre-processing input and output lecture, as well as the pre-processing quality assurance prior to deep learning model training lecture from last year. We'll upload the Google Colabs that's corresponding to these YouTube links as well here, but we'll just add the self-learning title in there. So that you know that this is for your own learning. But for today, this stuff is all here. If you have any other questions, let us know. Great. So I'll stop sharing. Is there anything else that you want to add?
I was going to say we do have some question on the chat for Dr. Azizi. So
Great.
First one is from Zahra. To compare the model's performance, do you use different split for each model, or you can use the same train and test samples?
So you should keep your test set separate after you do your grid search by cross-validation. You find your best model, then you will test your best model on your test set that you had separately. You shouldn't really train on that. So that's how you can compare the performance of your like different train model on your same test set. You don't change your test set or combine it with your train at all.
We had also an earlier question from Mustafa, which I think you did explain during your presentation, but maybe you could re-explain it again for everything to be clear. So Mustafa asked, would you please differentiate the test, train, and validation data?
Yes, so usually you can create 3 sets: train, validation, test. And your validation can be the one that you validate your grid search on that, or you can do cross validation on your train set. So these are like optional. People usually have a different set for validation, and at the end they try it on a test set, or you can just have train and test and do your grid search with your cross validation, and then finally test it on your test set. So these are the 2 ways that people usually do.
Wonderful. Do we have more questions coming up? If not, we want to just thank.
I
No,
think
we do?
Sorry, Jake, I think there is one on the chat from Benjamin.
Oh, go ahead.
Do you have any recommended resources for learning about different clustering approaches?
I'm not sure. I think we can. There was a book about like different clustering. I will find it and send it to the guys to share it with you in the module.
Great, thank you.
Okay, fantastic. Yeah, so I don't think we have more questions regarding the lecture today. We just want to thank Dr. Azizi again for your very valuable time on Sunday for us, and the wonderful lecture as well. And we'll definitely keep in touch. For everyone in the chat that's saying that you can't really open the Gumroad platform, don't worry. We'll upload everything on Google Drive again, just to have available options for you, so that if you can't open Gumroad, you have the Google Drive for all the materials. So I think that concludes for today. The next session will be next Saturday, again at 10:30 Eastern Daylight Time in the morning. We'll have our supervisor, Dr. Shireen Anger, and the CEO of a company called Exactus to speak to us next Saturday. And then after that, we'll have a Sunday workshop again. So meanwhile, during the week, you should look at the platform and familiarize yourself with introduction to medical image preprocessing before we move on to the next part. All right. Thank you so much, everyone. Have a wonderful rest of your day. Thank you so much again, Dr. Azizi.
My pleasure. Have a great day, everyone.
You have a lot of thank you on the chat. Yeah, so
yes.
Thank you very much, Dr. Azizi.
It's my pleasure. I'm glad it was useful.
Have a great Sunday.
Absolutely.
Have a great Sunday.
We hope to have you again next year.
Thank you. Yeah, hope to. Bye.